Okay, hi everyone. My name is Alfonso Ladino, and I'm excited to share the work that we have done on improving the management of weather radar data using cloud-native solutions and FAIR principles to make data not only accessible but also impactful for decision makers and the scientific community. So a little bit about me. I'm a grad student wrapping up my PhD at the University of Illinois. Sorry. And yeah, I've been working with radar data for, I don't know, like 10 years now, maybe. And yeah, something that I've learned from working with this data is that not all the time, not always, not often, the difficult part of working with radar data is the science. It's actually the data. So let me explain why. So let's start with this. Yeah, before we dive into the data side of things, so I would like to quickly walk through how weather radar works. So what you're seeing in this animation is a weather radar doing what it does the best. It's just spinning 360 degrees at a constant elevation angle, and then measuring data such as reflectivity, which help us to see precipitation mainly. After one sweep, the antenna actually tilts up to a higher elevation, and then repeat this process over and over multiple times, all the time. So together, those elevations, if we put them together, they will form something like, if we could imagine, like a donut shape of the atmosphere. So this is the measurements of the atmosphere, and then we know this as a VCP, as a volume coverage pattern. So I would like you to keep this in mind because we are going to revisit this term, and then we're gonna explain why this makes the difference. So yeah, as I just mentioned, this VCP repeats every few minutes. Thank you. It might be between 5 to 10 minutes, depending on the operational part. And then this creates a regular measurement. So this should be ideal for a time series analysis. But this is if we manage the data properly. So, okay, let's start with some common applications. So the first one is the one that we already might know. We use it for real-time application, which means it's like we translate single measurements into actionable insights. So all of us, we want to know when a tornado is coming, and that's where this approach is like really useful. So yeah, this support like severe weather detection and precipitation monitoring, precipitation monitoring as well as aviation safety. But when we shift to long-term applications, the things get more complicated. So in this case, it's not anymore about creating like instant products, but now it's like analyzing years or even decades of data. So unfortunately, yeah, so this is ideal for climatological studies and machine learning. So all of us, we wanted to do machine learning on huge data sets. That's why we won. But unfortunately, as the data is stored in binary format, so this is creates like a difficulty, like several problems, especially if you are doing a large scale analysis, which means that you have to do like a massive input-output operation just to prepare the data, even before when the science begins. So yeah, to understand a little bit about this problem, this is a huge problem, I would say. Let's look at this map. This is the coverage, the world coverage of around 809 weather radars operated by 91 countries around the world. So this data comes from the latest radar database from the World Meteorological Organization, the WMO. And I would say this is a massive observational network. So if you could imagine all those radars like spinning around, capturing data of the atmosphere, this is a lot. But here's the thing. So only 3 national networks like actually provides access to the data through platforms like Amazon, like S3 buckets, like open access. So unfortunately, this is just about 20% of the all radars worldwide. So those are the NEXRAD, the US NEXRAD radar data, the Finland Meteorological Radar Network, and also the Colombian Radar Network, the place where I come from. So yeah, technically the data is open, but the data is not fully fair, and this causes problems. I will tell you what kind of problems. But now the question is, what about the rest? Yeah, the data might exist, but also the data might be restricted, offline, or buried in a hard-to-access archive. So yeah, unfortunately, we cannot access. Now I want you or us to focus on the US NEXRAD network. I would say this is one of the most long-term running system, if not the most. It is at least 100, it has around 160 radar data, And yeah, thanks to the NOAA Big Data Partnership in 2016, the full level 2 historical archive was transferred to Amazon Web Service to the Open Data Program. So the initial release included data from 1991 until 2016, totaling about 270 terabytes of data. So which was in that time around 180 million files. And then if we fast forward to this year, February of this year, the data has grown till like 870 terabytes of data. So spanning around 360 million of millions of files. So I would say that this is an incredible volume of rich atmospheric observation, arguably a treasure trove for meteorology, climate research, and data scientists, of course, machine learning as well. So here's the catch. The data is accessible, but, and a huge but, unfortunately, the data is stored in a binary raw format files, compressed files, as you can see here. So what I'm showing you here is how the data looks like in the Amazon S3 bucket. So as you can see, it's like individual files, compressed files, not interconnected, basically not fair data at all. It's just open data, but it's not fair data. So unfortunately, this limits open science. So basically, this creates accessibility barriers. We need to do, if we want to do some analysis, we need to download the data, which means that we have to do duplication. We need to duplicate the data. And then unfortunately, that's limit the very promise of open science, which is terrible. So, okay, why the key reason why this data remains fragmented is the operational complexity introduced by BCPs. I remember that I asked you to keep this in mind. And basically, BCPs are designed to adapt radar scanning strategy, to specific weather conditions. So you're looking here is in the left-hand side, a radar facing a beautiful storm. So the radar will operate differently if it is facing a clear air sky, as you are seeing in the right-hand side picture. And let me show you why are such differences. So here we have in the bottom of each picture a vertical transect of the scanning strategy. So you have in the x-axis, you have the range, and the y-axis altitude, and each colors might represent the elevation, the scan elevations, right? So for example, for the precipitation mode, you start usually at 0.5 degrees elevation in the antenna, and it goes up to 19.5 degrees elevation angle. So it might be around between 14 to 20 sweeps, but then it all depends on the scanning strategies. And then on the other hand, we have the clear air mode. It just goes from 0.5 till like 0.5 degrees elevation, like way more elevations. And guess why? And this is because, yeah, as we are not facing any sort of like weather or meteorological echoes, we don't want to spend energy, like pulses to the atmosphere. So in that case, what we just do, what the operational meteorologist does, is they increase the sensitivity of the sensor, which allows them to like see atmospheric boundary layers such as fronts or even biological scatter. So that's how people do bird migration. I don't know if you have heard that we can do bird migration with radar data. That's the way that we do it. So yeah, because such variability and complexity in different BCPs, we haven't been able to create a unique ETL process, like extraction, transformation, and loading process, to create or consolidate a unified radar data set. So unfortunately, this creates a lot of complexity. So, okay, so the good news came in 2018 when the World Meteorological Organization released the FM 301 data format, radar data standard format. This model provides a hierarchical structure for radar measurements built on top of NEXRAD FCR radial data model and aligned with the climate and forecast convention. So this hierarchical model organizes or structures the data in this way. As you are seeing here in this picture, 3 levels. At the root level, we have the global attributes and the ancillary variables. At the node level, we have like the suite measurements with the suite level metadata or attributes. And then at the leaf level, we have data variables, the actual radar measurements, radar reflexivity, vertical or radial velocity, and associated metadata. So yeah, in 2014, last year, this was implemented in Python via XRadar library, which allows us to handle or give a structure to single radar files. So now we have an structure file, or in this case, object. And then here, this was built on top of the Radar DataTree model. And then here, a big shout out to Tom Nicholas and the NEXRAD team for releasing this data model, which is kind of the last one. Still, we have data raw files. We have given raw files a structure, but still we need to deal with thousands or even millions of files. So still we have an issue. Okay, so to address this, so I would like to introduce you. The solution that we are proposing here is something that we call the Radar DataTree model. So basically, this is another hierarchical structure that unifies the radar scans into a coherent, scalable, and data set, preserving the structure of each BCPs. And then I will present an animation, and then hopefully with this, I will show how this data tree works, or how this model works. So we start with thousands or millions of BCPs in the cloud, currently storage in the cloud. And then what we do is we use an ETL process to create a BCP, a hierarchical structure, sorry. And within this hierarchical structure, each BCP is represented in one different node, right? So this allows us to keep all those BCPs in separate. And then every time that we have another BCP is gonna be concatenated along this corresponding node. So this will give us the opportunity to create sort of like a time series radar data. So now that we build this radar DataTree model, and now we live into the XRA domain, we know that we can just do 2SAR, and then we will have an analysis-ready cloud-optimized data set, right? So this is how the data looks like. So you have in the top the SAR folder, and then each node will represent a BCP. So in this case, it's gonna be BCP 11, 12 to 12, and then within each BCP, you will find every sweep measurement for each, BCP, sorry. So, okay, so yeah, now we got a structure, we got the model. So now we wanted to test this data model. So we are gonna use something that is called the quasi-vertical profile. Basically, this is a technique introduced by Risk Capital in 2016. And basically what this does is giving us the opportunity to get vertical structure, information of the vertical structure of the storms, basically by taking usually the 20 degrees elevation angle, and then taking the average or the average of radar data. Could be reflectivity, could be cross-correlation ratio. I mean, other variables around the full 360-degree sweep. So we can do this for multiple timestamp, and this will allow us to create sort of like a time height product. So now we can see how is the vertical structure of the storm. So the idea with this data model is to try to generate this figure with the legacy, download and process model with our proposed Radar DataTree model. And for doing this, we're gonna use the Oklahoma QVNX radar data to reproduce this figure from Risk Capital figure 4, and then this event took place in May 2011 between 10 to 12 UTC. So, great, so now let me show you how this radar DataTree looks like. So as you can see here, we don't have anything, we don't have any single files, everything just lives within one XRA store. And then everything is only in just one data tree object with multiple groups. In this case, each group will be a BCP. In this case, we have 11, 12, and 32, which are clear air modes BCP, and then the 212, which is the precipitation mode. So yeah, when if we want access to the data, we just use a simple file path, in this case, it's gonna be, I wanna go to the BCP 212 to the lowest elevation angle, and it will return us a data set. In this case, this data set has the radar dimension, the time series dimension, and then if we look at the variables, it is CF climate forecast convention compliant, which means that we have rich metadata. Also, the data is chunked for efficient subsetting, parallel processing, and this is also give us the opportunity of having seamless integration with tools like Dask for elastic computation. So yeah, now we can say that we have a data set which is self-described, which is standard compliant, analysis ready, and then also is cloud optimized, right? Okay, so now let's compare both approach. So here what you are looking in this slide is that you have in the left-hand side our Radar DataTree model. In the right-hand side is the traditional workflow where you have to go, get your file, download into your computer, and do all the process. And then the first thing that I would like to point out is that we successfully reproduced the image from Rich Capital in both cases. But also, the thing that I like to point out as well is that the computation time. So for our data model, it's just 1.5 seconds in contrast to nearly 6 minutes that it took to the legacy model. So yeah, this represents something like 210 times faster than legacy model, like querying data, downloading data on a traditional standard hardware configuration, like my laptop, basically. So yeah, this new Radar DataTree model enables workflows that now are collaborative, reproducible, inclusive, and promotes open science and open data sets, basically. Yeah, we had the opportunity to showcase this the Radar DataTree model in the real-world settings last year in the European Radar Conference that it took place. It was held in Italy, in Rome, sorry. Yeah, and then using radar data from Italy, we demonstrated how this ARCO-formatted dataset can support collaborative learning and reproducibility. As a part of the open radar short courses, as you are looking here, this is available if you wanna check this short course. You can, thanks to Patia, you can execute this on the binder. You can just go there and check it out. But then, we work with a group of students that we guide them through workflows like quasi-vertical profiles, as I just showed you, but also quantitative precipitation estimation, which I think is one of the main uses of weather radar data. So yeah, here you have our workflows, and here is the interesting thing of this is that all of this we could do this without downloading data or even transforming file. It's just sort of like a plug and play science. So we just point to the bucket, and we just say, hey, just give me the mean around this dimension. For those who attended the ice chunk, workshop, you know what I'm talking about. So yeah, basically, this was a hands-on experience that we just didn't teach students radar things, but also we introduced them to the principles of open, fair, and scalable science. So now transitioning into the takeaways and try the conclusion. So our model is then a step forward to making radar not only accessible, but also impactful for the scientific community and decision makers. Also, this DataTree model successfully organizes data into this hierarchical structure following the meteorological standard data model, and is fully compatible with FAIR and cloud native principles. As we just showed, the time series at each node enable fast and scalable analysis without doing any massive input-output operations, just translating into really fast computation time. The downside of this approach is that our new ARCO-FAIR data tree has to be, leads to a data duplication. So we have been talking to Tom about using virtualizer on this, but unfortunately it seems to be like it's not going to be possible because this is binary compressed format. It doesn't follow like sort of like a range bytes. It's just like mess of information data. So yeah, we cannot use basically virtualizer for this. So we need to do data duplication, but this might be a trade-off between the benefits that we gain out of converting this data. Then finally, this was built for Colombian radar network, but it can be successfully, and also was successfully implemented to NEXRAD, but it can be implemented to any world, like, National Radar Archive. Even for, I was in this talk from Julia, this could also be applicable for the Sentinel data. So yes, with this I will finish my presentation. I'll be happy to take any questions.
Hi, that was a great talk. You mentioned applicability to national radar networks. Is there any interest from you or the folks at the Department of Energy ARM program to apply a similar concept to their transient field campaign radar networks? Just how did that work better?
Yes, I've been collaborating with with Argonne. I know they are running now Crocus, and they want us to apply this data tree to Crocus dataset. So we expect to have data in analysis-ready, cloud-optimized data tree format. Yes, so that's the idea.
Great, thanks.
Mm-hmm.
All right, great talk, really exciting. Did I understand that there's about a petabyte of this data now in S3? Is that about the total data volume for?
Yes, as you can see here, look, this is in this, oh, sorry, maybe it's not showing.
No, it is actually on the left there. Sorry,
yeah, so yeah, here we have, for the NEXRAD, is almost, I queried this data in February.
Yep.
Now we are in April. I guess we are now near the 900 terabytes of data. So
Amazing.
It's like, we're getting close.
All right, so yeah, then one more, maybe a follow-up question is, how did you do that? Like, how did you create, what was the processing pipeline like to do the data conversion?
You mean, I mean, I just took a small subset because,
Okay,
yeah.
The whole thing hasn't been done.
Yeah, I mean, this is a humongous data set. This is a humongous data set that I won't be able to run on my laptop. Yeah, no.
Yes.
This is just a sort of like a proof of concept, I would say.
You're
Yes.
giving me ideas. Thanks.
Thank you.
Are there tools that use the data in its binary format a lot? I'm just thinking of like duplication. Like, are there reasons to keep the compressed binary stuff around at all, or would it just make sense to, zar it all and then delete the original stuff?
Yeah, I mean, let me see if I understood. Is there? Second,
are there currently lots of tools that interface with the data in the current format that would not be able to interface with it in ZAR?
So, okay, so this takes me to my previous question that I did to Sarah, which is, are you using radar data? And apparently not much, like, companies are using radar data because such an ugly format. So I don't think much person are.
So, yeah.
Yeah, they are using this data. I mean, I know, for example, the MSMR, like multi-radar, multi-sensor product, is using radar data, but I guess their workflow could be easily integrated to this data set because, yeah, we are just, querying like data quite easy. Mm-hmm. Thank you. Any other questions? If not, thank you once more.